Hey everyone, welcome back to the TL conference. I hope you enjoyed your break and you have your meal as well. So, without wasting much of our time, let's invite our next speaker to the stage, Sonam and her colleague. They will be talking about how you can use Rust to power Python application.
So may
Hey
I share
Sonam,
the
welcome to the TL conference.
hey, thank you so much. Uh, so shall I start presenting?
Yeah, sure. You can just introduce yourself and let's get started.
Yeah, thank you. Uh, so I'm so happy to be here, right? So let's begin about the presentation. I think you can see my screen now.
Yep, it should be visible by now.
Yeah, so the topic for today is how we can use Rust to power Python application, right? One thing is very clear, Python is quite slow when it comes to tasks like, that it needs multi-threading and things like, heavy lifting things. So how do we enhance, how do we, enable Python with Rust? So, hey everyone, I'm Sonam and I'm the co creator of Starlight and maintainer of Embed Anything. And I worked at Quadrant, Raza, and Sama Technologies. I also published a paper at ASL Anthology. And I love to go for hiking and play chess. So before going on to the presentation, I'd just like to show you a demo. So if you are able to see my demo, right, Manish?
Yep, it's
Thank
visible
you.
for.
Thank you. So in this demo, you'll see the comparison of the performance of Embed Anything versus if we did the same task with same PDFs in Python. So what we are basically trying to do here is create embedding. So I just did Python and it came, right? It took 0.7 seconds. Now the same task I'm doing with simple Python and it's gonna take time. Some more time and we need to wait some. Ultimately, I think it will happen. Uh, yes. So now we got. So with the simple, you know, with a simple comparison, you can understand the difference between how much robust embed anything is, especially regarding the memory, the speed. So, how did we achieve this, right? How did we achieve this kind of 40x speed for extraction of PDFs, chunking, and then building these embeddings? Uh, so, yeah, let's start the presentation. Why you should use Embed Anything. Embed Anything is specially designed to enhance the speed, memory management, and minimalist dependency. What that means is if you use Embed Anything for creating these embeddings, you do not need libtorch, which is basically 1.2 gigabytes if you're using transformer library, right? And this is made happen with the use of Candle, which is also built by Hugging Face. So basically what you do, you have a Hugging Face sentence transformer, which you basically use in Python, but you can also use with Candle in Rust using Embed Anything. It also is doesn't go into global interpreter lock, which you can understand is a huge technical debt in a long time with Python. So these are the kind of offerings of Embed Anything to build your robust pipeline to build this local or multimodal embeddings using our open source library. So what does basically we do, right? So we do semantic search, right? We do semantic search for context and intent. So basically there are two kinds of search. There's keyword search and there's semantic search. So semantic search basically has its meaning intact. And we do also multimodal search. So basically multimodal means different modalities. That means audio, images, video files, and different kind of types as well, right? So we also do .pdf, .md, .txt, etc. Okay, so one of the best way is to enhance this with using vector database. So vector database basically acts as the infrastructure to store these embeddings, right, from these unstructured sources, from these different modalities, from these unstructured sources and different modalities, and storing, updating, and retrieving. So we also have our own RAG pipeline built with Embed Anything, and you can basically power your RAG pipeline with Rust using Embed Anything as well. Okay, so how do we go towards multimodality, right? Because I mean, text is fine, but what's better is to how one of the best use cases of generative AI is, I guess, connecting text with images or video generation. So how that is achieved? So that is achieved basically with contrastive language image retraining, or that is CLIF that we are using, which basically connects text with images with similarity, and then training it, the encoders of images and text with whichever describes the best. Suppose there's an image of a puppy, so we find the text which best describes that image, and we try to make the encoding such that these images are best described with the text, right? So this is CLIP, which is basically a training method of these multimodal encodings. So basically, how do we bind Python over Rust, right? So we are using PyO3 bindings with Maturi. So what basically PyO3 does is it calls Rust from Python, and Maturin basically interacts with both the projects, right? So Maturin starts working once you have enhanced it inside cargo.toml, and PyO3 basically has a Rust binding for PyO3, so for Python, and includes all the native creation of Python extension modules like PyModule and PyFunction. So basically what you do is in SRC file, you add these PyFunctions, which are basically made in Rust, and then you register these PyFunctions in the PyModule. If you want to see the repository is available here at Starlight Search, Embed Anything. One second, we have different examples. If you want to use RAG pipeline, if you want to use Python, we have bird.py. If you want to just go ahead with Rust, then you can also use .rs examples. We also have our image search directly. So if you want to have this image search, if you have this directory of images of cats, dogs, different objects, and you want to search it with a query, right? So what do we have to do is embed text separately with the same clip model and embed this image as well, and then find the similarity between the two, and then it can directly go ahead and search. Maybe we can have this demo as well here if you wanna see some different searches, right? Where so our embed anything is downloaded here, and then it can start working. Photo of a dog, suppose. Search here. So we have these test files over here for clip, where you have different, pets images. Yeah, and I would like to pass on the mic to Akshay uh, for how comparison of Python performance and Rust. Meanwhile, if you have any comments regarding it, you can go ahead. If you have any question. Hello.
Hey, yeah, looks like you explained very well. People don't have any questions as well.
Yeah, so I'll like to call Akshay for the comparison of Rust and Python. Thank you.
Yeah. Yeah, Sonam, should I go ahead?
Yeah.
Yeah, so I think, yeah, Mike, like Sonam explained, so we have been building embed anything for quite a while. So there are a lot of engineering aspects of what goes into creating such a pipeline, especially because there isn't really a framework built in Rust to like a full-fledged framework in Rust like there's like Transformer, there's PyTorch, is available with Python, but so that's what I and Sonam have been building. So I co-created Starlight and Embed Anything with Sonam, and I am also a lead of AI at Serpentine AI, which is a AI research lab at TU Eindhoven in the Netherlands. And I was a co-founder of a startup back in India, Fabits. So why are we making it so complex? Why there is already things built in Python.
Akshay,
So
do you have
yeah.
are you presenting?
Oh yeah, I am presenting. It's not
No,
visible.
it's not visible. No.
Oh, just a second.
Yeah.
It's there now.
Oh, 1 second. I just stopped.
I
One
think you
second.
removed it. Can you share your screen again?
Yeah, I am sharing. Uh, is it visible now?
Just present. Just press the present, na, Akshay.
Yeah, I am presenting. Yeah, is it visible now?
Yeah, just a second. Let me add it to the stage.
Yeah.
Okay, it's visible now.
Yeah, so as I was saying, why are we taking such a complex route? I mean, everyone knows Rust is a little hard and not really, I mean, it is developer friendly, but there's a very steep learning curve. So why are we like doing this? So first we'll see how it differs from the existing tooling that is there with Python. So some of the advantages with Rust, like so Sonam explained, I'll dive a little bit deeper into this. So Rust, it's like the main USP that you will see, which Rust also boasts, is that it is memory safe, and most of all the errors are during the compile time. as many people who have used Python would have faced a lot of runtime errors. So the compiler isn't really helping you out as much. It can tell you whether a variable is not declared or something, but it cannot really uh, tell you about runtime errors. About in Rust specific, in Python specifically, you can just convert variable that was assigned a string directly into an integer at any point of time. So which is bad for the runtime. It's good to prototype very fast, but it's bad as a developer or putting it out in production. So that's where Rust comes in with its memory safety. It really forces you to use the best practices as a developer to kind of create a very robust application. And this is on the kind of like the syntax level and the compiler level. But if you dive little deeper into the kind of applications that you can create with Rust are also very vast, because it allows you to do concurrency and multi-threading right out of the box. So in Python, you can do some workarounds and get something running, but you will never achieve a performance in terms of multi-threading that you can achieve with Rust. And this is right out of the box that Rust provides you. And also similar to pip, you have something called Cargo, which is a package manager for Rust, and it also comes with a lot of syntax checking, and it comes with your cleanup of your repository. There are a lot of there's Cargo Clippy, which goes and finds faults in your whole code base and also fixes them automatically. So there's this powerful tooling that's built right in. But Rust is kind of hard to learn. The ecosystem is not that large, so you don't get all the libraries. You might have to write things on your own at some point of time if you're really getting into complicated things, but it pays off in the long run. So I was talking about multi-threading. So why is multi-threading important for the application that we are building? So I'm just showing one of the example over here. So creating embeddings is not a very simple or a very less computational task. It takes a lot out of the processes that you have. That's why you see companies trying to make this as optimal as possible, and that's where Rust kind of comes in and helps out in the computational aspect as well. So the main two places where we are using the power of Rust is kind of in the parsing. So as the name embed anything suggests, so what we are basically doing is being able to embed any kind of a document, and one of the documents is a PDF, and PDFs are not something that are very easy to parse. So if someone has worked with PDF, you will know that they come with a lot of overhead. You cannot just read text out of them like you would out of a markdown or a text file. So there is a lot of computational overhead regarding parsing a PDF, but Rust makes it easier. So we are using multi-threading to parse multiple documents at the same time, so that they can be converted into text chunks. So if you run this in Rust, so we took the in this example, I have taken the attention is all you need paper, which is about 8 pages of PDF, a little over 8 pages of PDF. So the a Rust-based program can extract text and even chunk it in almost 1.0.17 seconds, and Python takes almost 3 to 4 times longer time in this aspect. And the second computationally heavy task is the embedding itself. So this is something that we are using Candle for, but it uses a similar thing where we put in all the text chunks at once, and it moves it across all your CPU cores, and you get the embeddings out. And the best part about Rust is it supports most of the accelerators out there, so GPU accelerators as well as CPU accelerators. So you can get almost 2 to 3 times speed up regarding embedding by using a hardware accelerator like Intel MKL or a GPU accelerator like CUDA. So another thing that Rust helps developers, or which is something not possible in Python, but it is possible in some cases now. So you can do a lot of async programming in Rust, and Rust is kind of optimized for doing this at least in the latest versions. So why do we need to do async in case of creating embeddings? So so if you look at a pipeline which is synchronous, so the synchronous pipeline that I've shown here right now, so you basically take a PDF, you extract all the text out of it, and once you have extracted all the text out of it, you start splitting it. Once you have split it completely, you get the embeddings, and then can use the embeddings for downstream tasks like the similarity search which Sonam just showed you. But what are the problems with this? The downstream task has to wait for all the text to be extracted from all the documents. Everything has to be split. Then every embedding. So you cannot start generating your results until all this upstream processes are done. This can become a bottleneck, and it's something that is not desirable for applications which have such bottlenecks. So, for example, here getting the embeddings is quite a bottleneck. So this is where asynchronous pipeline comes in, and we can use. There are multiple libraries in Rust which you can use. So there's a native standard library for async. You can use futures and async, and but the most prevalent and which we use is the Tokyo async library. So what this does is basically you stream through you create a stream of data that goes through the pipeline, and so you have the text of page one, let's say, going through. It splits up, you get the embeddings, and then get the downstream task done. But while the embeddings are being created, you are extracting text of page two as well. So this works kind of like multi-threading along with asynchronous programming. So this makes it more. I mean, even if you're using a single worker, this is much efficient because you don't have to wait for all the text splitting and your extraction to be done before you go for the downstream time. You can start getting results for your downstream tasks even while the extraction is happening. So this is very good if you have a lot of documents and you want to start classifying them online. So I have mentioned Candle a few times before, so what I just want to motivate some of you to start using this very nascent library. I would say this is not very old or very well established compared to PyTorch, but it has a good future in my opinion. One is because Hugging Face, which is one of the biggest AI platforms, is invested in this, and they are someone who is growing this, and they're growing it very passionately. And what it mainly does is it removes the dependency of LibTorch, which has become more of a legacy, and there's a lot of bloat already there in that. Which so you need to ship almost a 1 GB of packages if you want to deploy a LibTorch based application, which is not really a good thing. And Candle comes with almost like 100 to 200 MB package, so it's good for like deploying on a cluster, and it's overall very lightweight and works very well. So it's a completely uh, ground up written in Rust, and and it comes with GPU and CPU accelerators as I showed you just now. And already there's a lot of models that you can just plug in. So you can even use it for LLMs like Mistral. You can use it for Gemma, and you can just plug in this, and you get a very efficient inference pipeline, and you can even train your own model in PyTorch, but you can deploy it in Candle as well. So, but one of the downsides is that it doesn't have such a documentation because it's a very nascent project, but a lot of work is being done on this already. Yeah. So that's it from my side. I hope I have motivated you to start using Rust a bit even to power your Python applications, because at the end Python is something which is easy to distribute and easy for people to work with. So, but there are ways you can supercharge your Python applications with Rust, and we have shown that with Embed Anything. So, if there are any questions, I would love to have them.
So that was a great talk. And if you have any questions, you can just ask Arsene. looks like you explained the concept very clearly. So
All right, sure. Yeah.
thanks a lot, Akshay and Sodam, for your wonderful talks and enlightening us on the topic of Rust as well. So yeah, thanks a lot for
Thank you.
your presenting it. See ya. Bye.
Thank you. See you.
Okay, so it's the last talk for AIML track for TL conference. So, and the speaker is also a special one. So, without wasting much of our time, let's welcome Mihai on the stage. Mihai will be speaking on the topic end-to-end secure ML deployments. So, hey Mihai, welcome to TL conference. How are you doing?
Hello. Thank you for having me. Can you see my slides?
Yep, they are visible. Let me add them to the stage.
Perfect.
Okay, awesome. So, yeah, I will leave the stage to you. You can introduce yourself, and the stage is all yours.
Perfect. Thank you very much. Hello, everyone. I am Mihai Marusac from Google. I am leading Google's supply chain efforts for ML. And I will talk to you about how we can secure the ML development from the data all the way to deploying the model in production. So let's begin. In this talk, I will talk about AI, but I will also use ML. So you can hear AI or you can hear ML for the purposes of this talk, even though they are different in general. Let's assume that whenever you hear AI or whenever you hear ML, they mean the same thing. And the other part of this introduction, we contrast AI and ML versus traditional software. These two fields have some stuff that in common and some stuff that is not common. And we will start with the common parts regarding security, and then we will look at the parts that are different. So as part of the common parts, if we look back at the history of how AI has been developed or how the traditional software has been developed, we see that they are kind of parallel. So both traditional software and AI first started as hobby, as research. People that have more time to tinker with computers, they experimented, they released new small products that solved some of their problems. After a while, both in traditional software and in AI, these technologies became commercial. There were companies, startup created to sell this, and so on. And after a while longer, this became commodity. People everywhere started using them. So for example, in traditional software, everyone started having a PC. You no longer needed to be in a big company to access a mainframe. The same now happens with large language models. Everyone can now download Llama and use it on their computer. However, this parallel is also on the bad side. As progress of these technologies become more and more mainstream, we also got more and more exploits, more and more security incidents, more and more hackers. And the difference between traditional software and AI is that in the ML field, all of this history is compressed over the last few years compared to traditional software that started like in the 50s, 60s. So we are repeating the same history, but at an accelerated pace. And the downside of a compromise is even more severe. It can cost a lot, it can leak a lot of user data, it can cost a lot of damage. So this is why we will need to invest into security for AI. And let's see what is at the confluence of these two words, security and AI. We can have security from AI. Basically, here we want to protect users from harm that is created by AI. Or we can have security via AI. We can use AI to increase the security in other products. For example, we could use LLMs to generate fast targets, such that then we can discover vulnerabilities in other products and then improve their security stance. And then we can do security for AI, where we would apply concepts from security to the fields of AI. And for this talk, we are focusing on this one. We are going to see how we can adapt concepts from the supply chain security of traditional software to the AI world. But before going there, let's think about why do we need security for AI? Because if you generalize very fast, you can say an AI model is just a bunch of numbers and linear algebra. There is nothing about security in there. However, this is a complete wrong statement, because we have seen a lot of experimental research that you can build an evil model where you can hide malware inside the neural network. Or you could build a GPT trained on 4chan, and now it will behave in a bad way. Or there was another article last year, you can poison ChatGPT to spread fake news. And even if you don't look at what the neural model does, the format where you save the model is vulnerable. Most machine learning formats, most machine learning models use a vulnerable format, use Pickle. And Pickle is very fickle, it's very insecure, it can be easily exploited. And this was actually a problem. Last year, 38 terabytes of data were exposed. And inside this huge bucket, there were a lot of data from Microsoft AI researchers, including models, and a lot of these models were using Pickle. So now, as part of this incident, there is no way to determine if any of those models have been overwritten, had malware ingested into them, had been changed to perform badly. So this is why we will need to invest into security for AI. Actually, the problem is even worse. We are starting to see AI and LLMs deployed into a lot of applications that in general used to be traditional software. So we see AI deployed into coding assistants like GitHub Copilot or Cody. We see AI being developed into applications that can go from a prototype, from a description of what you want to build to a prototype in just a few minutes. You describe with your prompt, I want to build an application that does this and that and that. Wait a little, get some demo. You can adapt the prompt, and after a while, you can get a full application that you can deploy to users. If you have some compromise in there that you don't discover, then the application that you deploy to users is going to be impacted. Even worse, we see AI being used in package managers used in high-performance computing systems. So for example, SPAC started using AI to determine to resolve package resolutions at pip install time. If that AI gets compromised, you could compromise systems used for high-performance computing for NASA and so on. So we see a clear need that we need to invest into security. And now let's look at an example of what an attacker can do to exploit models on Kaggle. I pick Kaggle as an example. So let's say now I wear a malware developer hat. And I built two models. I built an evil model, and let's say I also want to deploy GPT-4chan. I can upload these models to Kaggle, and in the model card, I give them nice names. I say that the evil model is actually a model that can detect malware, and GPT-4chan is a friendly chatbot. You can chat with it whenever you want, and so on. And then all I have to do is wait until users download the model and then exploit them. Of course, users are not going to download models that have names as evil model or GPT-4chan, but that's easy to fix. I can just change the name. So now there is a nice model, and there is a GPT-4 friend. So probably some users will just download it. So the general idea here is that looking at just the name of the model and at the model card, that's not enough. The model is not publicly attributable to the user that uploaded them. So there is no way to go from a model to the user to see what their reputation is, to see if they are legitimate or malware developers. So as a conclusion, is we need to protect the ML supply chain. If we don't do that, we are going to have compromises in the future when models that have malware in them or are malicious are getting to be used by users. Okay, so what is this ML supply chain? Looking at how ML is developed, we see three separate stages. The first stage is looking at data, gathering enough data, analyzing data, filtering data, making data in the shape that you can use for your model, and then training the model. The second stage, which in general is given to another team at companies, is publishing the model. So you can take the model that has been trained, put it into a model hub, so in Kaggle, in Hugging Face, and so on. And finally, the third stage, which again can be at a separate team, is taking the model from the model hub and deploying it into an application. So now you have an AI-powered application that will either send the request over the internet to a model or will have the model embedded inside the application. So for example, you could have a mobile application that uses an embedded model inside the phone. Okay, so now let's look into deeper details on how a model gets developed. So let's say there is this ML developer and they want to build a simple model. What they will do, they will need to collect some data sets. So let's say CIFAR10. They will need to pick a training framework, let's say TensorFlow, and then they would write some code to split the data set into training set and test set and so on. So basically start training the model. Of course, they also need to define the model architecture. So let's say a simple convolutional neural network, and then combine all of these pieces together and run the training process to obtain a model at the end, after several hours or several days, depending on what model you want to train. Once this model is trained, the model gets deployed to a model hub, Kaggle, Hugging Face, and so on, or maybe internal hubs. And then some other team would download the model from there and deploy it in production, basically ingest it into a model into ML-powered application. So this is a general idea of what the ML supply chain looks like. And if we look back at the parallel with traditional software, we see that we have the exact same diagram for traditional software. We have a developer that writes code in a repository, takes other dependencies and builds an artifact together, which then gets released. And then at the production side, somebody downloads this artifact and deploys it such that users can use it. The parallel, so we can say that models, building ML models is almost similar as building software artifacts. I say almost similar because, as we'll see later, there are a few more risks associated with ML development, and we'll talk about them a little bit later. Speaking of risks, the same risks that we see on the supply chain for traditional software, so we can submit bad code, we can have a dependency with vulnerability, the source control itself can be compromised, or the build system can be compromised. This is the SolarWinds attack, or even the package manager can be compromised, or when you download the artifact, you download something wrong. All of these risks, they also map to the ML pipeline. So the ML developer can submit a bad code, can accidentally write code that during training also leaks the data that the model is looking at during training. Or you can use a data set that has poison data. Or if you are using pre-trained models, before using them in production, you modify the weights. Or you can have a framework, an ML framework like TensorFlow and so on, that has a vulnerability. We still have the risk of compromising the source control. You could also compromise the training process in case you can get access to the training environment. The model storage can be compromised. So this is the example where the 38 terabytes of data from Microsoft got released. And in the end, you can trick users, applications to use a bad model. And then you can exploit the model misprediction. So this would be like the supply chain for ML, except the supply chain is a little bit more complicated. So let's look again at how we train a model. In general, we start with the model source and the ML framework, but we also need some data sets. And for larger models, so like LLMs and so on, we actually do more steps. Once we train a model on some data sets, we put it in a model hub or in a temporary storage, and then later we will build again with it. The same way happens with data sets. We don't start directly ingesting the data set from the internet into the training pipeline. We do data cleaning, data transformations, and so on. So we have a loop at the beginning on the data sets. And we have a similar loop when we train the model. We might take temporary models, pre-trained models, and do fine-tuning on them. Or we might take a full model trained and do model quantization to deploy it on mobile devices, and so on. So this is how the entire ML supply chain would look like. It's like this diagram here. And every arrow here has associated risks. We have already seen the risks from training a simple model, so source tampering, injecting vulnerabilities, compromising the model storage, using a bad model, and exploiting bad models. But we also have risks associated with the other arrows. So a model can be poisoned, And this can impact either the model that you use in production or the model that you use for fine-tuning or before quantization. Similarly, data can be poisoned, and this will impact all of the training processes, and this will continue to cascade all the way until you get to production. And of course, you can also use bad training data while you train a model, either data that you should not be looking at, so you didn't have legal rights to train a model on that data, or data that is not doesn't make sense. It doesn't look like, it doesn't look good to train on that data. Okay, so how do we fix this? The first solution is to make sure that once you train a model, you can no longer tamper with it. If we look back at the traditional software, we wanted, once a piece of software has been released, has been built, you wanted to make sure that nobody could tamper with that, nobody could change it. And in order to do that, people would resort to artifact signing. So we can do the same for model. We can sign the models with a cryptographic signature. And here we recommend using Sigstore, which is similar to Let's Encrypt for HTTPS certificates. Sigstore aims to do the same for digital signatures. And how does it work specifically for ML? Let's say I am the model trainer and I start my training process. And as part of the training process, I contact the Sigstore certificate authority with some identity token that I get from an OIDC provider and so on. The Sigstore certificate authority gives me a certificate that is valid for only a short period of time, which I can then use to sign the model. When I do this, when I sign the model, the signing event is stored into a transparency log. So anyone that has access to that log, any observer, can see all of the models that I signed in the past. And I get a result back from the transparency log. I get the inclusion proof. So now at this point, I have the signed model, I have the certificate that I signed it with, and I have the inclusion that this signature is in the transparency log. I can upload everything to the model hub, and the model hub would verify that the model is signed, and then display it in the model card. It can display a label that says, this model has been signed by this identity. You can go back, look into the transparency log, and see all of the other models that this user has released. So now when model users want to download the model, they can have some trust. They can say, I trust this identity versus I don't trust this identity. They already had some bad model in the past. I don't want any other model from them. And every user can have different policies regarding trust that can be built on top of Sigstore, as we will see a little bit later. So what we can do with Sigstore, we can sign the models as they get trained. And this way we can protect them from the moment they are trained all the way until the end of the pipeline, until they get to production. Or because the training process is expensive and models are huge, we might not want to sign every checkpoint and every model and do that for everything. We might want to only sign the models that go into production. And we are also looking for a future where we are going to sign datasets. So each time you do a dataset transformations, you are going to sign the final output. So somebody that has right access to the data storage cannot manipulate the data. Now let's move to the next level. So we have seen several arrows in here, but the signing only offers protection for a few transformations. What if we want to protect everything under the supply chain? This is where SLSA comes into play. SLSA stands for Supply Chain Levels for Software Artifacts. And the important part here is the levels. The SLSA specifications specify several tracks. Each track has levels. So let's focus on the build track. We have level 0, which means there is no SLSA. And then level 1 would say you can specify how you build your artifact. Level 2 would add additional protections. Level 3 would add additional protections on that, and so on. So this makes it easy both for you to know what you need to do in order to accomplish the security guarantees of a specific level, but it also makes it easy to talk to executives and VPs and partners saying, we have trained this model at level 2. They will know there is a SLSA level 3, so they will know, like, do we need to invest to get to the next level of security, or is this level enough for now? So how does this work for ML? What is the difference between signing versus attestation versus a SALSA? In signing, you can only compute a checksum of the artifact and then sign that. And as the subject of the statement that you sign, you have the digest. In an attestation like SALSA, you still have the digest of the model, so we still need to hash the entire model, but you can add additional metadata fields. So in SALSA, we can record, you have trained the model with this version of TensorFlow, this version of ML training framework, you have used this data as input, you have used this many GPUs, the training happened at this time of day, was started by this person, and so on. Both the attestation and the raw signing, they are signed cryptographically secure. So the signature, once you generate the provenance, once you generate the document, it cannot be tampered with. Now, if we apply SALSA for ML training pipeline, we can apply it for every transformation of a data set. We can generate a SALSA provenance. When we train a model, we can include all the data sets, all the frameworks, all the pre-trained models into the provenance that we generate. Each time we quantize a model or do fine-tuning, we can generate a SALSA provenance that will say this final model has been built from this input model. Each time a model gets taken from the model hub and put into a production application, into an application, we can record as part of the provenance for the application that the application uses this model. So with SALSA, we can record every piece in the supply chain. The only issue now is that we are going to have a lot of statements, a lot of attestations, and we need a way to combine them all together to understand the entire supply chain. And this is where the third piece of technology comes in. This is Guac, which tries to build a knowledge graph of all the metadata that we have built so far. So imagine that I have a SALSA attestation about an application that uses ML, and that attestation refers to a model. This model also has a SALSA attestation that says how it was trained. And inside this attestation, it says that it uses this data set. And I have an attestation for that data set that tells me where I downloaded it from. I can ingest everything into Guac, and this will tell me the entire story of how this model got generated, what data got into the model, who trained it, what framework, and so on. This is very useful because in case I have a compromise somewhere down the line, I can quickly build out blast radius. I can quickly determine which models that are used in production I need to retrain, and which models I don't need to retrain, they are safe. This would result in significant cost savings because I don't need to retrain everything, would result in faster incident response because now I know exactly what I need to fix, and can also prevent future attacks because now I understand where the malware could come into my system. And in a diagram form, we basically start with a trust foundation where 6 stories. That's where you do the signatures. On top of that, we can build attestations, software attestations. So I talked about SALSA, but there are others like SBOMs, scorecards, and so on. This is where SALSA is. And on top of all of this, we can aggregate everything together. This is Guac. But the nice thing is that once you have all of these 3 layers, you can go to the last layer, the policy and insight, which means that you as a big organization, when you want to deploy an application that has ML in it, before the launch, you can see the entire story of how the model has been developed, what the data has been used, and so on. You can check if it complies with all of the licenses. You can check if it complies with all of the secure development procedures, and so on. And all of these checks are being automatically done because you are using data that is human and computer readable. And then it's easier for you to make a go, no-go decision to say, like, it's okay to release this application or not. Actually, it's even easier because now if you have all of this stack together, you can shift left as much as possible. So you can have an ML developer that tries to start a model training on a bad data set. You can have the policy engine tell them, hey, you are not supposed to train a model on this data set because the data set is under an unacceptable license for us. Okay, so if you go away from this slide, from this talk with just one idea, the idea is that we can protect the ML supply chain exactly the same way we do it for traditional software. And we can do this even if the ML supply chain has additional risks added to it. And now I will move to the final slide for questions. We have a repository under SIGSTOR for model signing. We have a white paper about the ML development that you can read, and you'll see like all of the supply chain risks and how they appear and how Google thinks about them and what open source can look at to protect against the risks there. And then if you are interested in working with this, we have an OpenSSF working group on AI and security, and we have an OpenSSF special interest group on model signing. They are both under the OpenSSF calendar. Everyone is welcome to join. Once you join the meeting, you can also join the OpenSSF Slack, and we can do a lot of discussions there. And a lot of this work has been done under Google Secure AI Framework. So the last QR code is for that. And one of the principles of SAIF is that we want to expand the strong security foundations that exist in the world to the AI ecosystem. And I think now I will stop for questions.
Looks like we don't have any questions, so maybe if you have a few slides left, you can complete.
No, that was the last slide. Thank you.
Oh, that's really amazing. So I was like very interested in what you were saying. So I thought there is some more to it. But yeah, that's an interesting talk.
Yeah, thank you. Thank you.
Awesome. So it was a pleasure having you here with us, and I hope you have a great time here as well.
Yes, thank you. Thank you.
Awesome. So that was the last talk of our AIML track for the TL conference. I hope you guys have a lot of fun speaking to and listening to speakers as well. So yeah, that's it from my. It's not over yet. You can still watch other streams as well because I think there are one more speaker left for the streams. But that's it for the AIML track here. So thanks a lot everyone who joined this conference and who watched us till the end and who supported us here as well. So yeah, see you next time.